Let's add and subtract radical expressions. What we mean by adding and subtracting radicals is a lot of times we do that with square roots. What that means is we're going to take expressions that have square roots or cube roots or radicals in them and try to combine them as much as we can. Now, it's worth noting that we can only combine the terms that have the same index and the same radicand. So we can't just straight up add two things until we get them so they have the same radicand. In other words, we might need to simplify before we do. This works a lot like variables. So if we had 2x plus 5x, if they already match, then we can combine them by adding the coefficients and we get 2 plus 5 is 7, so 7x. That's the same way it would work as if we had a square root of 2 in there. But I want you to know that they have to match up, okay? Which means we might need to simplify to get them there. So let's look at 4 examples. First up, we have this set of radicals, and I'm going to go ahead and tell you they can't be simplified because I can't simplify square root of 6. But what I can do is I can combine like terms. So I want you to notice that we have a square root of 6 and a square root of 6. We have minus 4 and minus 5, so that's going to be negative 9 square root of 6. I don't change the square root of 6. I leave it just like I wouldn't change the x if it were a variable. And then I have the other two pieces. Now, that's just going to be plus 3 square root of 11. Okay? Now, let's make it a little bit more complicated. Let's see if this tricks you. Here, you'll notice that I have square root of 5. Actually, I have square root of 5 and cube root of 5. Notice that these have a different index. Those have a 3 up there. A cube root of 5 is not the same thing as a square root of 5. So when I do this problem, I'm going to treat each of those like a separate variable. But again, I'm just adding or combining the coefficients, and I'm leaving what's in the radical alone. I'm leaving the radicand by itself. Now, to kick it up a notch, now we have one with variables. So what we want to do is recognize that they both already have x to the 5th in them. So I'm tempted to want to be able to combine them. But before I do that, I'm going to want to simplify each of them. So if we simplify the first one, I'm going to say the square root of 50x squared, x to the 5th. If I look at just the 50, that would be 25 times 2, right? And so the square root of 50 is the same as square root of 25 times square root of 2. Square root of 25 is just 5, so that would be 5 square root of 2. Notice that I already had a negative 2 out there. So if I'm just looking at the numbers, this first one ends up being negative 10 square root 2. Now, there's more than just numbers there. You'll notice that we have an x to the 5th. Since the index is a 2, this is a square root, that means I can't, how many sets of 2 can I get out of there? Well, I can't get an even number of x's. There's an odd number of x's. So that means there's going to be one x left in there, but I can get 2 pairs out. Okay? Let's take a look at the second example. Sorry, the second part of this problem. We have, let's see, 9 times 2 is 18. So the square root of 9 and the square root of 2 would be the same thing as square root of 18. That's going to be 3 square root of 2. But you know that we already had a 5 out there, so we're going to multiply it. And that gives us 15 square root 2. And just like the last one, we have that x to the 5th. So I'm going to simplify a little bit and have x squared on the outside and x on the inside. At this point, we can now combine all this business because what's right here, our radical, is identical. What's in there is identical. So I'm going to combine them. And in order to do that, I'm just going to combine the coefficients. And I have negative 10x squared and 15x squared. So I'm going to get 5x squared square root of 2x. In this problem, we have to the 3rd power, so we're going to have to do something a little bit differently. But when we pull these out, what we're looking for is something that is cube rooted. So something that's multiplied. So I'm just going to factor tree this whole thing. I'm going to try to pull out all the factors. So I know that 54 is 27 and 3. Nope, 27. 20, what is it? It's not 27, it's 27 and 2. There we go. And then we have 3 and 9 becomes 3 and 3. And so if we were to factor tree that, we pulled it out. Our final set of factors is the ends of these nodes. So I have a set of 3 3s and a single 2. Now that means I can pull the 3 3s to the outside, which is just going to be a 3 on the outside. So I'm going to do 3 times 4 is 12. And since I'm looking for a cube root, I wanted sets of 3, but there's only 1, 2, so I'm going to leave that alone. Okay. If we follow that same pattern and we go ahead and look at the second one, what can I take out of both of those? Well, I can take a 2 and an 8 and an 8. I can take a 4 and a 2 and a 2 and a 2. I've got 4 2s, but I'm going to look for groups of 3, and then I have 1 left over. So guess what? I'm going to take a 2 and put it on the outside and multiply it by what's already there. So minus 18 cube root of, and we still have a 2 left over. Now the last one is the cube root of 9. So I'm going to say 3 times 3, and I can't go any further. So guess what? I have both of these, but this is not a set of 3. So I'm going to leave that as just the way it originally was, okay? I can't actually simplify that. Now at this point, you might notice that we do have something that can simplify, is that both of these say cube root of 2. So we can combine them, and we end up with negative 6 cube root of 2 plus 5 cube root of 9. Try these out. Do not get carried away oversimplifying. On that fourth example, you notice that when we finished, still had multiple things. They didn't all crunch down into one number. And so similarly, you want to look for these that they're not going to all crunch down to the same thing. Just do the best you can at simplifying each one and then combining like terms. Like and subscribe so you get updates whenever I post these.